Good morning to everyone and welcome to this webinar held by Conself. We are an Italian company and I am Ruggero Poletto. Our mission is to provide you with design software easy to use and accessible everywhere. And by accessible, I mean flexible from the usage point of view, but also from the pricing. We offer CFD solutions on cloud, consulting services according to your designing problems, support both on software and for designing, engineering problems, but we also organize events such as this webinar, and we also offer training for specific software both on-site and on remote. Before going through the tutorial, which today is going to be about heat exchange in electronic cooling, let's have a quick overview of Conself CFD software. Our software is a cloud software, so it is available on a browser without license and with hardware provided according to the requirements, to the needs you have in that precise moment. And in general, we can estimate that by using Conself, you can save up to 90% compared to standard CFD software. The advantage of using simulations compared to experiments, they are huge. First of all, there is no limit on the number of elements you can simulate, but there is also a huge decrease in costs, in particular by using cloud solutions, because we don't have to create a prototype and go to a test lab in order to get the results. We just need to provide the CFD software with a CAD file. We're going to see later which are the interfaces between the CFD software and the CAD software. And by using this file, you can simulate anything you need. It's worthwhile mentioning that there is also a time restriction compared to test lab. Since we don't have to create prototypes, we don't use people time, we just use computer time. So we decrease the overall cost and overall timing in order to get results. Obviously, the main issue regards the accuracy of the simulation, but an expert user or a guided user with Conself support can actually reach very good reliability for his simulations. In our software, we define 4 phases. The first one is the CAD phase, is the phase in which you generate the geometry and select how to define it. Then there is a geometrical phase in which you subdivide your fluid volume into geometrical entities such as cubes or triangles, and in this way you can create a mesh or grid. There is a CFD phase. In this phase, it's like we are defining how we want to run the test. So we specify the inlet, outlet, temperature of the fluid, pressure. We specify all those parameters we would have to define to a lab to run the test. For instance, in our case, we have to specify what is the heat flux we want to extract from the CPU. And then obviously there is the results analysis. In this phase, we get all the data created during the simulation and we analyze them in order to understand whether they satisfy requirements or not. Let's talk a little bit in details about the features of Conself. We can interact with a multiple input file format from CAD files such as step file, IGES file, or STL file, which are now very popular for 3D printing. It is possible to use multiple unit system. As we know, users are from all around the world, and some of them, they use the international system, some of them are based on imperial system, and some other on other unit system again. Going to the meshing test, it is possible to define two types of meshing. One of them is hexahedral, another one is tetrahedral. So one is based on squares and the other on triangles. For both of them, it's possible to define a boundary layer, which is a zone very close to the wall, which defines reduced size of cells useful to detect the velocity gradient close to the wall and thus increase accuracy of the simulation. In the CFD phase, we have the possibility to interact with multiple flow type, so it's possible to simulate incompressible flows or ideal gases. So in the counterpart experiments, it would be possible to use water or air, or anything which is liquid or gas. Moving on, it is possible to use multiple mathematical models for turbulence, such as K epsilon, K omega SST, and Spallart-Almaraz. And it is possible also to define whether we want a static or transient simulation. Our results are highly reliable as they are based on the open source software OpenFOAM, which is the biggest open source project in this field and is validated by many universities and in particular by the ESI group, which is the group that actually develops this software. Also, from the post-processing point of view, we have the most common tools available online, such as slices, streamlines, profiles, and contours. And obviously, it is possible to download screenshots and data from the server. I just want to remind you that Concept is not just a software. There is much more involved with that. First of all, the support we mentioned earlier, but there is also a database of test cases and tutorials available on our wiki at wiki.concept.com. As I said before, we also provide you with hardware resources from our cluster. These resources are potentially unlimited and they are available 24/7, so anytime, day or night. We also offer a software development service in which, according to the characteristics of the simulation you need to run, we may develop extra features on our CFD software. But before proceeding, let's move a little bit closer to the tutorial we're going to face. As you read from the title of this webinar, the tutorial is going to be about CFD electronics. In particular, we're going to investigate the heat transfer in an electronic component, which is a CPU, and we need to extract some heat, some excess heat from this particular tool. Having a closer look at the geometry, we can actually see the CPU with all these flanges attached to it, and these flanges, they increase the heat transfer from the CPU to the flow. It is possible to visualize the flow, which is going to be in the same direction as the flanges. And obviously, I don't have to mention it, but the zone where the heat is produced is the entire CPU. Let's move now to the practical example we have just seen, and let's see how we have to interact with the CFD software in order to get to the results and analyze them. So just give me a few seconds so I can swap. Here it is. So this is the consult website. I am using a standard browser. In my case is Google Chrome, and I am on a Windows 8 operative system. As I'm going to say also later, we don't have limitation according to browsers or to operating system. You can use our platform from anywhere you want. I moved to the website, concept.com, and obviously I'll log in to our web application. I need to provide my user and password. Obviously, if I don't have any, I can register and get a new one. So once I log in, I can have access to the web application, to the CFD web application. There is the dashboard, and we are going to talk about this a little bit later, because in this way we can understand a little bit more in details what's going to happen in the dashboard. And there is the simulation page. From this page, we are going to create a new case, and we are also going to interact with the software in order to define the parameters, the geometrical parameters, and everything we need to set up in order to run the simulation. On the left bottom corner, we can see that we have access to the user manual, but also to the support I mentioned before. So everything is embedded inside of the application. So first of all, let's turn on the manual and let's see what's going to happen here. We are redirected to the consult wiki, in which we can actually understand how the application works and assess all the functionalities which are in place in the application. It is possible, obviously, to interact with them and read all these sections. And with a graphical output that can make it easier for unexperienced users to use our software. But at the same time, as I said before, we also provide you with a huge number of test cases. If you click on tutorials, CFD applications, under HVAC, heating, ventilation, and air conditioning, it's possible to access the electronics cooling, which is our today's tutorial. In here, you have summarized all the details we are going to see later together, but also you can download the step file from which the simulation starts. So moving back to the application, I can now create new cases. We are going to call ENG elect and 18/11/2015. So I created the application, sorry, 18/11/15. I can create the application, and the first step I need to complete in order to run the simulation is that obviously is the geometry step. I need obviously to upload the file, so I just select the CPU file I previously downloaded. And here it is uploaded in a few seconds. After that, we have to specify the file units we have created for that file. In our case, we generated that file in millimeters, but I could see multiple choices from miles to inches to kilometers, centimeters, and obviously meters. Then I have to specify how to divide the file. Generally speaking, we created color surfaces on the step file in order to detect the boundary in later steps. Having specified that, we have to go to flow type and detect whether we have an internal or external flow. In our case, it's internal, and submit the job. I'm asked to confirm my choice. Here it is. The process runs in background, and we have a progress a percentage of the progress available, and also an estimated time for arrival. So with this, we have under control the whole process. For time reason, I need to move a little bit faster than the software, so I'll upload a simulation I previously ran for you, and I have already run geometry in this tab, and we can actually see what the software did in geometry before proceeding with Mesh 2D and looking at the details of it. Here it is. This is basically the visualization of the step file. I can get a clip with which I can look inside of the step file, and here it is. With the clip, I clearly understand that this is the CPU with the heat source. This is the wall that surrounds the CPU, and this is basically the fluid volume that interacts with the heat produced by the CPU. In here, as you can see, I have a boundary selection, and then I have two parameters, the uniformity level and the max element size. First of all, let's specify what are these two parameters. Basically, in this step, we want to create triangles on the surface. We want to create the surface mesh in order this to be the first step towards the complete volume mesh. So we need to specify what's the size of the triangle and what's the uniformity of the triangle across the surface. So let's first check what's the CPU yellow boundary. What is it? So let's move back to simulation.foam. Let's activate only the yellow boundary here. Press apply. And we can see that the yellow boundary is the flow that surrounds the CPU. And for this, we have to specify a 90% uniform and a 0.005 meters, so 5 millimeters for the resolution of the surface mesh. Let's move to the next boundary. It's the dark orange one. Once again, let's visualize it. We can actually understand that this boundary consists in the wall of the fluid that surrounds the CPU. For it, we just leave the uniformity level to 70, and we select a 0.05 5 centimeters wall resolution. Let's move to the blue boundary. So blue. Once we click OK, this boundary represents the top of the volume of the fluid, and to this boundary we apply the same resolution we gave to the dark orange one, so 5 centimeters. Last but not least is the red zone, the red boundary. This is basically the CPU. So we need a very high resolution, so we increase the uniformity level, and we apply the 0.0005 as max element size. So 0.5 millimeters is a very small resolution, and this makes you understand how accurate we want this result to be. So now I should click submit and then confirm the submission, and then wait for the Mesh 2D phase to finish. But for time reason, let's move forward to the Mesh 3D phase, where obviously we can see the result of the Mesh 2D, the previous step we have just set up. Once again, we can see the geometry, but this time I can actually visualize it according to the surface with edges. And thus, I want to visualize the triangles, in particular to understand the sizes, whether they are corrected, to have also a feedback. Here it is. These are the sizes of the triangles. As I did previously, let's create a clip in order to enter inside of the mesh. Let's color in surface with edges once again. Here makes us understand very, very clearly that we are having a more refined mesh grid space close to the CPU rather than far from it. This is coherent with the decision of having in this zone the maximum heat transfer between the CPU and the flow. So let's move forward and let's decide the meshing algorithm in order to better understand what is the difference between the two of them. Let's go back to the manual. So wiki, and let's click on manual. Here it is. These are the two meshing types. On the left-hand side, I have hexahedral mesh, and on the right-hand side, I have a tetrahedral one. So the first one is based on squares, and the second one is based on triangles. For the purpose of this simulation, let's stay focused with the tetrahedral mesh, and let's use resolution this time for the volume elements inside of the domain of 5 centimeters. This resolution is similar to the maximum surface size we applied earlier. Let's move on, where we have to define the boundary layer. The boundary layer is the wall resolution as we approach a concrete surface. This wall resolution consists of a certain number of layers of cells, and starting from a wall cell height, a given wall cell height. And by defining these two parameters, I can completely define this boundary layer. For the purpose of this simulation, let's just leave the default value, 0 and 1. And then we can submit the job and run the mesh 3D this time. So we are gonna fill the volume inside of our domain. Let's pretend I did that, and let's move to the CFD phase, where I can see the results of what happened in the mesh 3D step. Let's just wait for the mesh to load. This time, once again, I'm gonna make a clip of my domain and color the clip with edges. But there is gonna be a massive difference compared to earlier. This time, the mesh, it is also inside of the domain. So this time, I finalized the whole volume mesh with a more dense region close to the CPU or the flanges, and a region with a minor density far from it. Now we are ready to decide the CFD setup of the simulation. So let's start from the density model. We need to decide whether we want an incompressible or compressible simulation. Let's stick with compressible simulation, because with this we can calculate heat exchanges. We also want flow viscosity to be specified. Let's choose a standard Spallert-Almaraz turbulence model. Now we have to define the fluid properties such as Prandtl number, specific heat, and specific heat ratio. The default number refers to air, and so with that decision, since we are simulating heat extraction in air, we can just leave the default values. We also have to specify the initialization, in particular pressure, velocity, and temperature. We are going to start the flow with a temperature of 288 Kelvin degrees, about 20 Celsius degrees. And then we have to specify the dynamic viscosity of the flow. By selecting this parameter, we can define whether the fluid is air or a type of oil with a high viscosity, and obviously apply the Spallert-Almaraz for initialization. Moving on, the more interesting part is the boundary. In here, we have to specify for all the variables of our problem whether we want a fixed gradient or a fixed value specification, and the gradient or value for that particular variable. Obviously, Conself in the manual provides you a huge help in our choices, and in particular, with this table, we provided default values and calculation to be performed with some simple boundaries, such as inlet, outlet, adiabatic wall, or wall with heat transfer. By using this table, we are going now to set up the boundary conditions. So, as usual, we start from the yellow. So, since I want to visualize the yellow, let's go and choose sources, and let's choose the yellow surface. So I click apply. Yellow is the wall that surrounds the boundary, and as I said, it's a wall. So in a wall, we need to specify a zero gradient for pressure, a wall velocity, which is zero in our case for the velocity, and this, since we don't want heat exchange to happen at this particular location, we just define a temperature gradient to be zero, and the same for Spallert-Almaraz variable. We move on to the dark orange boundary. So once again, on the right window, I just visualize the dark orange. This is the box of the fluid volume. In here, since we are dealing with open air, we are specifying a standard air pressure of 101,325 Pascal, so 101,325 Pascal. And we also want to specify a certain velocity in the Z direction, the same direction of the flanges. Once again, no heat transfer and the turbulence with gradient zero. The next boundary is the navy blue. So let's visualize it. This is the top of the volume flow, or the volume of fluid. So once again, let's select the same atmospheric pressure as defined earlier and the same speed for the air. No heat transfer and turbulence as usual. Last but not least is the red 4. So red 4, this represents the CPU basically. So in this, we have a pressure gradient, we have no velocity, but this time we want to apply a gradient for temperature. How can we define it? Well, it's simple. We define a fixed gradient for the temperature, and this is the formula we have to use in order to calculate the temperature gradient. So heat flux divided by the area and the fluid thermal conductivity. So moving back and calculating it, I obtained this number 12,123. So 12,123, which is my temperature gradient. And then obviously the boundary condition also for scalar timers, as usual, they're going to be gradient 0. We can move to the final section, in which we can define whether we want a transient or a steady simulation, and the number of iterations, which for our case are 100, and the frequency, the output frequency, how many iterations exist between one solution save and another. We select 50. Now we are ready to click on the submit button. Before doing that, I need to specify that most of the time the simulation, the CFD simulation, is the biggest task among the overall simulation, and thus make sure that you have enough credits in order to run the simulation. Usually it takes from 4 to 10 hours to run this part of the simulation. Let's move then to the results. Here it is, I can visualize them. 1 second. Once again, we get to the same geometry we saw earlier, but this time, this geometry contains the solution we calculated from the CFD simulation. So this time, we can actually see what happens inside, and thus the flow. First of all, let's cut a slice in order to see what's going to happen inside, and I want to print the temperature of the flow. By moving the slice, I can zoom in to the zone inside, and I can actually see that this red zone highlights a high temperature zone, which is actually convected in this white zone. This is the convection of the flow, the heat extraction from the CPU. In order to locate this slice inside of the boundary, inside of the volume flow, I simply define an opacity to be lower than 1. And here it is. Now I can see the slice and the CPU. But I'm still not happy. I want to get even more details, and thus I'm going to print streamlines once again from the same place, a stream tracer. This time I select, and with this one I just need to specify the location for these streamlines to start from. So I select a 0y coordinate, I press apply, and here it is, the streamlines. So with the streamlines and the temperature profiles, I can actually visualize the flow inside of the flanges and thus of the heat exchangers, and thus analyze how this flow can extract heat produced by the CPU. Let's move now to the dashboard. In here, now we can view and check more in details what's happening across in all these graphs. In our subscription, you basically are assigned a certain number of credits that you can use for the simulations. Our subscription goes from €200 per month with 200 250 credits, and they go up to 1,000 euro per month with about 3,000 credits. And in here you have a summary of how many credits you have remaining in your simulations and how many you have used already. And also you can have a preview of which simulation uses the highest number of credits. In here you can see that the webinar electronics, the one we have just seen together, used about 5 credits. Probably a standard simulation uses a bit more, but with 20-25 credits you'll be able to do it. And also you have a statistical overview of the steps you run in all your simulations. With this, I can consider finished. I can consider the end of the webinar. So we can move back to the presentation. And it's time now for the questions. So it's a little bit tricky making question with the Google Hangouts, but once again, click on the top right icon with multiple squares, and then on Q&A, question and answer icons, and then select once again, sorry, all right. So select question and answer, and then make us any question through the chat. All right, few seconds for the first questions to come out. So here it is, the first one, browsers and operating system. There is no a limitation on the browsers you can use, as we said earlier, and you can use the application also on mobiles, for instance, so no limitation for the operative system of your tools, of your equipment. We just recommend to use a big screen, because in order to interact easily with the graphical interfaces, this is the requirements. Furthermore, you need to have a CAD software in order to generate the CAD file from which the simulation starts. One question about the subscription. Yeah, it is possible to have a shared subscription. So it is possible for company to have a single subscription and use that single subscription for all your employees. Obviously, the advantage is that since it's a web-based application, you can run this software from anywhere and thus be more flexible with your employer, in particular with requirements to work at, I don't know, customers, locations, or different places rather than standard office, let's say. All right, one more specification about the cloud solution. Obviously, it is required to have a cloud network when you set up the simulation, but once the simulation is running, you can log out to the website, do something else, and get back only when the results are ready. All right, while we wait for some more questions, I'll just give you a few new contacts in order to talk and speak with us. We are online, present in the most popular social network, in particular LinkedIn and Twitter. We are also on YouTube, where we are gonna upload all the webinars we have already held, but also the ones we are gonna hold tomorrow. And I also remind you the website, www.concept.com, and also the email address you can use in order to make us any questions and comments about the topics we spoke during this webinar. So the email address is info@concept.com. I don't see any more questions, so I suppose I was good enough to reply and satisfy all your needs. So thanks for listening and looking forward to welcoming you to our web application. Have a good day.